What is the Miller indices? Miller indices in fractions. So Miller indices were introduced in 1839 by the British mineralogist William Hallowes Miller. The method was also historically known as the Millerian systems and the indices as the Millerian. So orientations of the surface or crystal plane may be defined by considering how the plane or interior or any parallel plane or intercepts or the main crystallographic axis of this solid. The application of the set of rules related to the assignment of the Miller indices HKL is a parameter, a set of numbers which is quantity of the intercepts that thus may be used in uniquely identify the plane or surface. That determines the crystallographic planes we take unit cells or three-axis coordinate systems. The three state of coordinates. Central principle. Here is the Miller indices in 0. The plane is parallel to that axis. The smaller Miller indices more nearly parallel to the plane into the axis. So larger Miller indices more nearly perpendicular to a plane to the axis. So multiplying or dividing a Miller indices by the constant has no effect on this orientation of the plane. When the integers used in this Miller indices contain more than the one digit indicates this must be separate by comma. So this is changing the signs of all indices of planes. We obtain the plane located at the same distance on this other side of the solution. In the crystal system, the unit cell is smallest repetitive volume or the contained unit the complete lattice pattern of the crystal. So 7 crystals and 14 crystal lattice. ABC are the lattice constants. See this here, directions or diagonals. This is the crystal system. This unit. The unit cell is the smallest component of the crystals that reproduce the whole crystals when stacked together. See this all the cubic structures of this body center cubic, body face center and end center and primitive. So see this primitive is the unit cell contain only the single lattice point. See this is a single lattice point. Another one is internal. The unit cells contain an atom in this body center. So center of point. So body center. So another picture is a center of body structure. And F is a unit cells contain atom in this all the phases of this plant composing the cell. So see this all the phases, 7 phases. This is a single phases of the center of point is the body center and the 7 phases of the center of point is the body center phases. C is a center. The unit cell containing the atoms center on the sides of the unit cell. See this and the another last one is the end to end. So end to end this corner of this end to end. They accompany the 7 crystal axis, cubic, tetragonal, orthorhombic, hexagonal, monoclinic, and triclinic, monoclinic, so tetragonal, so which is the crystal lattice. So this P, I, F, and C is this the unit cells of this simple lattice, body center, all phases of this plan, and the center of this axis plane. So this is a unit cell is the smallest component of the crystal that produces the whole crystals and the stack and the together. This Miller indices group of the 3 numbers that indicate the orientation of this plane, a set of parallel planes, the atom in a crystals. In the hexagonal systems, which is the 4 crystallographic axes and a similar scheme of the 4 previously Miller indices is used. See, this is the lattice parameter in cubic, orthorhombic, and hexagonal crystal systems. So how do you calculate the Miller indices? For example, if the XYZ is the intercept of this 2 and 3 and the Miller indices are called the reciprocal 1 by 2, 1 by 1, 1 by 3 clear fractions multiplying by 6. So is 3, 6, 2 is reduced to the lowest term of the already. See this is cubic, orthorhombic, so hexagonal. So this ABC is the angle, is hexagonal is the angle, degree is 120 degree angle. So this is the section. So basic definition of lattice sites, defining the basic terms and giving the examples such as the point is atomic position, Vectors define this particular directions or plan normal. Miller indices define this particular plan relation to diffractions. 3 indices of the cubic and 4 indices the notation of the HCB. So Miller indices are used to specific directions and planes. The directions and planes could be in lattice or crystal. The number of indices will match with the dimension of the lattice or crystal. See this crystal directions, origin 100 is the angle, xy is directions, see this and then see this new not in new origin, so reverse directions, negative, and another one is a crystal plane. So see this is if the plane passes through the origin, either the construct another plane, so create a new origin. And then for each axis desired where the plane intercepts or parallel the axis. Algorithm of the Miller indices rate of intercepts of the plane with the axis in term of ABC. They take reciprocal of intercepts reduced to smallest integer values. He includes the parentheses, no commas. So this is crystallographic planes. Crystallographic planes are specified by the 3 Miller indices HKL. All parallel planes have some same Miller indices. See this plane referred to this original at the point is 0. So is the other equivalent plane is 001. So this origin is a 001. So see this 110 is plane is referred to this origin at the point is 0. This slightly is different angle on this another equivalent of this 110 plane. So another third one is a 111. So plane is refers to this origin at this point is 0. So this is different angles. So this is equivalent other equivalent to critical one plane. So this is XY direction is totally different intercepts and so the crystallographic plane. So it is so Miller indices are symbolic vectors represented for the orientation of an atomic plane in a crystal lattice are defined as the reciprocal of the fraction intercepts which the plane makes with the crystallographic axis. To find the Miller indices of this plane intercepts the plane along each of the 3 crystallographic directions. So 1000, 010, 001, another is 111. So this is the crystallographic intercept determines the intercept of this planes along with this 3 crystallographic directions take the reciprocal of the intercepts. In fraction results 1 by 1 by 2 1 by 0. So multiplying each of this denominator of the smallest fractions. So this is see the crystallographic plane intercept. See this example A, B, C is the directions 1 by 2 is the fraction, so on intercepts. So is off of this cubic structures. 1 by 2 is off. 1 is one full entire is and 3 by 4. See this is 3 by 4 is almost off of this almost of 3 by 4 angle. And reciprocal is 1 by 2. This is divided by 2 into by 1 is 2. So another is 1 by 1 is 1. Another is 4 by 3. So this is the reciprocal sectors of the vectors. And this is a reduction. So this is and 3 cubical structures. So this is a phase and 3 multiplying is 2 into 3 6 1 into 3 3 and 4 by 3 into 3 is 3 by 3 is close to almost is clear and the 4 is given. Miller indices 6 3 4 is this is a crystallographic plane. This family of the plane. So see that this intercept reciprocal. So totally angles totally different of this intercept and reciprocal. So see this indices. So this is see that this and reductions and then so this all the part of this family of the lines. So planes. See, first same is 110, another one is bar is 110, another direction is reverse direction, another opposite direction is 1 bar 10, 1 bar 0, 1 0 1, 1 bar 0 1 bar, and 1 bar 0 1, and 1 0 1 bar 0 1 1 is totally all the direction will be slightly changed of this intercept reciprocal. So it will be changed on this plan will be in the will be changed. 0 1 bar 1 bar. So another one is 0 1 1 bar. 0 1 bar 1. So this is totally every direction will be. We are seeing this in the intercept and the reciprocal family of the cluster structures, the cubic structures on that time. So this is another one is a phase center cubic unit. So this is 110 plan. See this A B C D E F. This is structures of this. The phases, so sound cluster system, sound phases in cluster. So this is a A B C. So this is C the angles, the structures of another one is C that's dotted A B C C D E F. This is a phase center of the unit cell. This 110 plan. So this is a BC body center cubic unit cell. This is a 110. Already we are seeing this phase center cubic structures all the directions. So this is one of the main important point, center points. This is the body center cubic structures A B C D E. C is a center point. So this is the center atom. So the unit cell so is a body center cubic system. So this is one of the main lattice of this arranged on this the crystal systems. One there is example is 2 and example 1 is the intercept. So this is the angle of this crystal. So the intercept 1. The whole direction we have covered in this x and y is infinity and z is infinity. Reciprocal see this 1 by 1. So another one is a reciprocal. So 1 by 1 is a 1. They are giving to this ratio is 1. Another one divided by infinity is 0. 1 by infinity is 0. So middle indices 1 0 1 0. 1 0 0 is middle indices. Another one example is to intercept this totally differently angle. Actually, the angle will be slightly changed on this axis xy direction. So see this intercept x direction and y direction will be totally intercept on the reciprocal. So you see this one x intercept point is 1, yx and y is a 1 and z is infinity. Another is reciprocal is 1 divided by 1 is 1, the smallest, and reciprocal is 1 divided by 1 is 1. So this is a 1 divided by infinity is 0. So middle indices we are given to this 1 1 0. Another third one example is that this axis three different angle will be touched on this in this crystallography of the middle indices. So intercept is 1, x-axis is 1, y-axis is 1 and z-axis is 1. The reciprocal bracket is 1 divided by 1 is 1, y-axis 1 divided by 1 is 1 and the z is 1 divided by 1. So smallest radius is 1 1 1. So this middle indices is 1 1 1 triple 1. So this is all the direction will be around this edges of the corner of the atom. So this is a suitable one of the middle indices of this unit cell. So another example of force. So see that this which is the attached getting touched on this however, so in here all the corners will be touched on this atom. So see the axis of the intercept 1 by half of this. See this x and y directions and z directions half of this half of the touched on this spaces. This x directions off and y is full on cover on this edges to 1 and z is infinity. So reciprocal is 1 divided by 1 by 2 is divided by upper side is 2, 2 divided by 1 is 2 and then is 1 divided by 1 and 1 divided by infinity is 0. So million indices 2 1 0 is million indices. So million indices ratio. So this is a plane of intercept axis at this 3 bar 2 b bar 2 c bar c. This is so this is one of the cluster sectors of this interplane of the million indices. So see this 2 0 0 is the one of this crystallography of the center of the whole of this 2 0 0 1 is one of the million indices. And this 1 0 0 is already we have to see this example. One is 1 0 0 and another one is a 1 1 0. So we have to give the example. Shows we are seeing that this triple one is the one of the another one example. So all the examples we are already seeing that this is reciprocal intercept and ratio. So we are given to this and the indices we are given to this. See already you have to see this intercept axis A B C is axis and the vectors on the reciprocal number is 100 by 3. The intercept of the plane is this crystallographic point, the direction and the plans are specified in the stem of indices of the schemes. Materials can be single crystal or polycrystalline. Materials properties generally very high with the single crystals orientation on the anisotropic but are generally non-directional isotropics in polycrystal. So the single crystals oriented isotropic, anisotropic and isotropic systems. So generally non-direct, so isotropic, anisotropic. So polycrystals is randomly oriented in grains. Some materials can have more than the crystal structures which refer as the polymorphisms or holotropy. So this is a summary of the indices.